Hello, this is the first of two screencasts about trying to understand or get a clearer picture about interactions in analysis of variance, or ANOVA. This is part one, and all the information that you'll need for this screencast will be in the description below. What's the background to this? Well, I'm a teacher of statistics, primarily to psychology students, and it's clear that many find the concept of interactions quite a tricky one to get hold of. And so I'm trying to think of new ways to just talk about them. And actually, there were some recent blogs and Twitter exchanges which have prompted me to some new thoughts on this topic. So this was the blog, came out quite recently by Daniel Larkins, a Dutch psychologist who writes a blog called The 20% Statistician. And this was on effect sizes and power for interactions in ANOVA designs. I'll put the link to the blog in the description below. There was also a Twitter exchange started by Lisa DeBreen and responses from people like Tom Bagley. And that started me thinking about a way that we might think about interactions in ANOVA. Once again, the link will be in the description below if you want to look at that Twitter thread. So the key message, my first key message, is there is only one kind of interaction effect in ANOVA. It's what we would call a perfectly balanced crossover interaction, sometimes called a disordinal interaction. And I'm going to introduce a concept called a 2x2 interaction graph, which is going to be important. And this graph shows you what the interaction looks like in ANOVA. This perfectly balanced crossover interaction is like this. We have two factors here. I've called them A and B. You can substitute in any factors that you like, your favorites. And we're dealing here, just to start with, simply with a 2x2 between subjects in ANOVA, but actually any 2x2 ANOVA, it works. So factor A has two levels, 1 and 2, and factor B has two levels, 1 and 2. Here they depicted factor B level 1 is a blue line with circles, and factor B level 2 is a red line with crosses. And the interactions graph shows these two lines cross over perfectly symmetrically. So the overall mean is 0. And the overall main effects for factor A and factor B are 0. The second key message is that all other interaction-like patterns in those 2x2 interaction graphs, which we're used to looking at, we look at them and we see things which look like interactions, they're interaction-like patterns. They're actually a combination of a perfect crossover effect that I've just shown you, plus a combination of one or both main effects. And the direction and differing sizes of those effects in combination give you the graphs that you're familiar with. And that's actually, I think, quite a surprising message for some people. Staff, colleagues of mine, as well as students, are a little bit surprised about that. And why is this a surprising message? Well, I think we're used to making predictions for our experiments, our studies, regarding what the 2x2 interaction graph will be like, what that will look like, and not what the actual underlying statistical effects are that are actually estimated by the ANOVA. And there are a lot of different patterns that you can find in the 2x2 interaction graph. In fact, in one sense, there are 75 unique patterns for a 2x2 design. I won't bother to go into the detailed maths of how we get 75. In fact, that full set of 75 includes cases where the interaction effect in the combination is actually 0. We're going to need to talk about effect sizes in a 2x2 ANOVA, because each of the main effects has two levels. We can use a well-known measure of effect size called Cohen's d for each of the between subjects factors for each of the main effects A and B. So D is the group difference in the means between the two groups, expressed in terms of the standard deviation within each group. And as you know, ANOVAs like this require, these between subjects case, require homogeneity of variance between the factor levels. So these variances or standard deviations in each group should be approximately equal in order for the assumptions underlying the ANOVA to be met. So to calculate D, if these standard deviations aren't exactly equal, you can average them, but they should be pretty similar. So just taking an average will give you a rough idea of what the effect size is. We're going to see how these effects, main effects and interactions, are specified in terms of an effect size like this in the next few slides. And we'll work for simplicity with a grand mean of 0 for our data. I've talked in other videos about how it's useful to start simulating data drawn from standard normal distributions with a mean of 0 and a standard deviation of 1. And that's going to be the case here as well. So just to show you what that looks like, here we have our standard ANOVA table with our 2 levels of factor A and our 2 levels of factor B. They're color coded here. And basically this means that the average across all the cells of the table is 0. Now obviously in the simplest case there are the same number of cases in each cell, there don't have to be, and you just average them all, you get 0. If there are different numbers you need to use some kind of weighted average. So that's the grand mean. Moving on, now let's express using our Cohen's d the way that we would capture an effect for factor A such that the scores in level 1 were on average higher than the scores for factor A in level 2 of that factor. And so we can write it like this. We take our Cohen's d for main effect A, we split it in 2, we divide it by 2, and we add that half of it to level 1, and we subtract that half of it from level 2. So the overall difference between the groups is dA, which is what we want, and it's symmetrical, preserving our mean of 0. Okay, simple move. We do the same thing for factor B main effect. We have a d for factor B as main effect, and we add half of it to level 1 of factor B and take away half of it to level 2 of factor B, preserving the grand mean. Now it doesn't really matter which way round we do it. Here we've arbitrarily designated it such that level 1 has a higher score than level 2 for both main effects. And now finally, what do we do for the interaction? A little bit more complicated. Here we have a d for the interaction. What we do is we have the same occurrence at level 1 of factor B for the effect of factor A, d over 2, and then minus d over 2. And then for the other level of factor B, we simply have the mirror image of that, where the minus effect is here and the plus effect is here, producing that crossover that we saw earlier. That's how a perfect crossover interaction is specified. How do we get the various 2x2 interaction graph patterns that I've said are so varied and so important to understanding the link to the statistical effects underlying them? Well, we're going to combine our 3 effects for A, B, and the interaction A times B in different ways, and we get different interaction graphs, and we combine them in the 75 possible ways we get the 75 interaction graphs. In the graphs to follow, I'm going to use a single base effect size, which I'm going to call D, and I'm going to set it to be 0.4, just well convenient for a main effect. That would be a typical, slightly larger than typical effect in many areas of psychology. It's a small to medium effect in Cohen's typing of these effects into broad bands of size. And I'm going to show in the following slides some of the possible 75 2x2 interaction graph patterns. And I've developed my own numbering system for them because I like to do that kind of thing. It's not very important, but you'll see the numbers on the actual slides. So here are the interaction only patterns. Only an interaction effect with no main effects. There are only 2 such patterns. They're numbered 10 and 16 in my numbering. And we see in this case, we have no main effects for A or B, and the interaction is our effect size D. And then all we do to get the other pattern is we simply make D a negative quantity. We essentially flip the red graph from here around the center point, so it's now flipped the other way, and ditto for the blue graph that's now gone the other way. And that's caused just by changing the sign of the interaction Cohen's D int as I'm calling it here. Let's take another simple case where all 3 effects are present and are of the same size. There are actually 8 of these, and I've just shown 2, which in my numbering system are number 1 and number 3. And this is the case where all the effects are positive D's, dA, dB, and dint are all D plus D, and that's the pattern you get. I think some people are surprised to find that you need to get an interaction graph like this, you need all 3 effects to be present, and you need to be broadly of the same size to get a graph like this. Here and they're exactly the same size is what the graph looks like. There is an overall effect of factor B. We move from here to here. There's an effect which goes up from minus 0.2 to the average of these 2 points, which is 0.2, which is our 0.4 that we use as our standard for D. Look at the main effect of A. Here the points are averaging minus 0.2, and here the average is between 0.6 and minus 0.2, which is plus 0.2. So again, the overall effect for factor A is D, and the interaction is also D.4 to achieve this combination. And all we've done here is flip round one of the signs of one of the effects. Arbitrarily, I chose D, and here the B effect is flipped over. So that's just basically swapped the red line from here, has moved it up to the top, as in here. And these two are remaining to be positive. Here's one of the cases where there is no interaction. Here's two unequal main effects, and these are numbered 68 and 75 in my system. Here, dA is two lots of D. It's just a convenient way of making dA greater than dB. Here we have the main effects. So for factor A, the difference here is between 0.2 and minus 0.6, which is 0.8. So that is D is twice R 0.4, and the parallel line here is just shifted up, so the difference is the same. Now for factor B, we look at the difference between these lines. It's the same either from this point or this point. Difference between this point, and it's between 0.2 and 0.6 is 0.4. So that's true. And then we can do the same analysis here, except that now I've made dB the larger effect, twice as big as the effect for A, but I've made both of these negative. So this means you add a negative quantity to level 1 in both cases of each effect. Therefore, you're making level 2 higher than level 1. Over here, level 1, take factor B, was higher than level 2. Here, level 2 is higher than level 1. So in video 2 of this series, I've developed a computer program which allows you to play with these interactions and get familiar with the patterns and how to generate them. Allows you to simulate data for any of these 75 interaction patterns quickly and easily. At the moment, the program currently exists in MATLAB only, but various other versions in other systems will be created in due course. The details of the program and in future programs will be in the description below. So if you check that, you may see there's been an update and other versions have been added. So that'll be part 2. So what's the summary? Interaction effects are not what you might think. You may have a prediction in mind for a study, but you'll probably be thinking of a pattern in the 2x2 interaction graph and not the interaction effect itself, which is a statistical estimate based on a crossover interaction. And in fact, the interaction graph pattern that you're thinking of is actually a combination of the statistical effects of factor A, B, and the interaction A times B, with some of those potentially being 0. They're the familiar interaction graphs that you'll be thinking of. So if you can understand the above, you'll be better informed in deciding which statistical tests actually test your predictions. You may not only test the interaction if you're predicting an interaction graph of a particular type. You might well need to predict and test that there'll be main effects of A and or B as well. And so you would interrogate this properly to address your precise predictions. So thanks for listening. As usual, if you like the video, you can like it in YouTube and you can subscribe to the channel. And then if you do, you hit the bell icon and you'll get notifications of future screencasts when they're published. Bye for now.